Okay, so this is the next question that we have on the menu today. It is asking us, a trunk with a mass of 23 kilograms is on the floor. The trunk has a very small initial speed. The acceleration of gravity is 9.8 meters per second. So we're on Earth here. That's nice to know. What constant horizontal force pushing the trunk is required to give it a velocity of 10 meters per second in 20 seconds if the coefficient of sliding friction between the trunk and the floor is 0.63? Okay, so let's actually draw a diagram of what is going on in this situation, and then from that diagram we can make some mathematical moves to do exactly what we need to do. Okay, so we have a mass here, and we know that that mass 23 kilogram. 23 kilogram. Let's draw it as a box. And we are on a fairly smooth ground where the coefficient of kinetic friction, which is when it's in motion, and that is 0.63. Okay, so let's consider the forces that are going to be in this situation. We know that we have gravity because, well, it's not floating away in space, so we definitely got gravity. So that's Fg, and that's going to be equal to mass times gravity, equal to 23 kilogram multiplied by 9.8 meters per second squared. Okay, and that's going to be our Fg. And we're also going to have a normal force. I'll draw it in blue so it's a little bit more clear. Now, the reason we have a normal force is because, well, the trunk is not sinking through the ground. Okay, so the ground itself is providing a force that counteracts the gravity. And in this case, it's just going to be equal to Fg. Equal because no sinking into ground. Okay, fairly straightforward. Now it says that we have a horizontal pushing force. We're going to need to solve for that, but we're going to draw that in. It just is unknown. So let's call that Fp for F push. Fp, solve. And we have a pulling force, which is actually just the frictional force. And our frictional force is going to be our coefficient of friction. So mu k multiplied by Fn. And since we know that mu k, Fn has to be equal to Fg, we could also write this as mu k times mass times gravity. Okay, so we need to know what the net force is, and we can have the net force on this. And if we define our axes like this, x, y. I know you may not be used to seeing the x going towards the left, but you know, you can set the coordinates however you please. We know that the sum of the forces in the y direction has to be 0, and that there has to be a net force in the x direction. Net force purely in x direction. Okay, and our force has to must accelerate from, okay, so notice how it says has a very small initial speed. We're going to treat that as 0. Now, the reason why it's not saying the trunk starts at rest is because then we would have a coefficient of static friction. Now, since they gave us a coefficient of sliding friction, they have to say that it has like a non-zero initial speed. Otherwise, we'd be going with static friction, and that it would not be harder. It would be a little bit harder, but That's not something that we really need to worry about right now. So it must accelerate from 0 meters per second to 10 meters per second in 20 seconds. Yeah. Okay. So the acceleration that we're going to need is as follows. So we know that our acceleration is going to be our v final minus our v initial over the time that it takes for that change to happen. I believe that's how it's calculated here. Yep. Okay. So our initial is going to be 0. Our final is going to be 10. So here we're going to have 10 meters per second minus 0 meters per second, all divided by 20 seconds. And quick with the maths, we can see that this is 0.5 meters per second squared. Okay, so given this, this is in the x direction, and this will be going towards the left with respect to our diagram here. So we know that the forces in the y direction have to be 0, but we know we should instead find the sum of all our forces in the x direction and equate them to our mass multiplied by this acceleration. Okay, so forces in x direction is equal to their mass times our acceleration in the x direction. So we're going to have our FP, which we're trying to solve for. And this is positive because this is going towards the left in this case. So you can draw a little symbol like this, an arrow pointing towards the left with a plus to show that this is our plus direction. We could have easily put the x direction in towards the right, but it's good to be familiar with different types of coordinate systems. And we have to subtract our friction force because that's going the opposite direction. So first I'll write it as minus F. And we want to isolate that, right? FP is what we're trying to solve for. That is the main goal of the question. So to isolate this, we can see that FP is equal to negative F. Wait, never mind. It's not. It's going to be we bring that FF, the friction force, to the other side. So we'd have MA in the x direction plus the frictional force. Okay, so FP, as we're trying to solve for, our mass, it was given to us in the question, 23 kilograms. Acceleration in the x direction, we know that has to be 0.5 meters per second. We calculated that this way, and that was given to us. That originally came from, the velocities that we're eventually going to need to reach. So that's 0.5 meters per second squared plus the frictional force. Now from our diagram up here, we know that our frictional force is dependent on our normal force. We know our normal force is equal to our gravitational force. Okay, so we know that we have a mu k, coefficient of static friction, times mass times gravity. So our coefficient is 0.63 times our mass, 23 kilogram, times 9.8 meters per second squared. And that's our G. Okay, so once we find this calculation, this will be our force of our push required for this to happen, and that will be that. So we got 23 times 0.5 plus 0.63 times 23 times 9.8. And my result for this, 153.5 newtons. Okay, hopefully we have a similar calculation here. Yeah, just with some rounding stuff. We were only given two significant figures, so to to adjust for that, we should write instead Fp is equal to 1.5 times 10 to the 2 newtons, just to be a little bit more formal with our significant figures incorporated in here. Okay, so yeah, that is the solution. We just gotta balance the forces and get these dynamics equations. Setting up these dynamics equations of like the sum of all forces is very, very important, and quite often used, especially in like mechanical engineering or people who are into more of like architecture, that type of stuff. Stuff is very useful, but very cool, and this solution is good. Awesome.